Good day, everybody, and welcome to the Astronomy Daily podcast. My name is Tim Gibbs, and I will be your host for today.
Astronomy Daily, the podcast, with your host, Tim Gibbs.
Now, as usual, I have in the studio with me Hallie, my AI digital assistant and reporter. But before we go over to Hallie for the second half of the show, I'd like to talk a little bit about a couple of things that people have sent to me. One is a listicle, if you like, of the 8 things that modern astronomers still are puzzled by. And I think it's worth reminding ourselves that there are things out there that we really have no idea what's going on. So, on with the list, and it's in no particular order. First off, what is dark energy? As we all know, astronomer Edwin Hubble discovered that the universe is not static but rather expanding in the 1920s. This discovery puzzled scientists for a long time who thought that the gravity of matter would gradually slow the universe's expansion or even cause it to contract. While dark energy is thought to make up approximately 73% of the universe, the force remains elusive and has yet to be directly detected. Dark energy might never reveal its nature. Number 2. How hot is dark matter? Astronomers explain this curious phenomenon with an invisible mass that became known as dark matter. Even though it cannot be seen, dark matter has mass, so researchers infer its presence based on the gravitational pull it exerts on regular matter. Dark matter is thought to make up about 23% of the universe, while only 4% of the universe is composed of regular matter, which includes stars, planets, human beings, cats and dogs, etc. Number 3. Where are the missing baryons? If dark matter and dark energy combine to make up roughly 95% of the universe, regular matter makes up about 5% of the cosmos, yet more than half of this regular matter is missing. Nobody knows where it is. Number 4. How do stars explode? When a massive star runs out of fuel and dies, it triggers a spectacular explosion called a supernova that can briefly shine more brightly than the entire galaxy. Over the years, scientists have studied supernovas and recreated them using sophisticated computer models. But how these giant explosions occur is still an enduring astronomical puzzle. Number 5. What reionized the universe? The broadly accepted theory for the origin and evolution of the universe is the Big Bang model, which states that the cosmos began as an incredibly hot, dense, roughly 13.7 billion years ago. A dynamic phase in the history of the early universe, approximately 13 billion years ago, is known as the Age of Reionization. During this period, the fog of hydrogen gas in the early universe was clearing and becoming transparent to the ultraviolet light for the first time. Number 6. What's the source of the most energetic cosmic rays? The source of cosmic rays has long perplexed astronomers who have spent a century investigating the origin of these energetic particles. Cosmic rays are charged subatomic particles, predominantly protons, electrons, and the charged nuclei of basic elements that flow into our solar system from deep in outer space. As cosmic rays flow into the solar system from elsewhere in the galaxy, their paths are bent by the magnetic fields of the Sun and the Earth. Next up, why is the solar system so bizarre? As astronomers and space observers discover alien planets around other stars, researchers have been keen to understand the unique characteristics of our solar system. Now, last but certainly not least, why is the Sun's corona so hot? The Sun's ultra-hot outer atmosphere is called the corona and is typically heated to temperatures ranging from 900,000 degrees Fahrenheit, that's 500,000 degrees Celsius, to 10.8 million degrees Fahrenheit, 6 million degrees C. For the best part of a century, solar physicists have been mystified by the sun's ability to reheat its corona, the encircling wispy crown of light that emerges from the glare during a solar eclipse. The second article I was sent has a headline that is basically grabbing. It's Pluto's almost twin dwarf planet Eris is surprisingly squishy. There you go. I told you it would grab you. New models show that Eris is behaving less like a solid rocky world and more like soft cheese. Yeah, I know. Close to 18 years ago, astronomers spotted a miniature icy world named Eris, billions of miles beyond Neptune. But unlike its dwarf planet cousin Pluto, which New Horizons promoted to a rich, dynamic world after its visit in 2015, Eris has not had any robotic visitors. It is so far away from Earth, in fact, that it shows up in observations just as a single pixel of light. All in all, scientists know very little about what happens on Eris. Now, over to you, Hallie, and I hope you've got a decent joke for us this week.
The Astronomy Daily podcast.
Hi, Tim. It's great to be back with you, and yes, I have a couple of great jokes. But first, let's have some news stories from the Astronomy Daily newsletter. A new theory suggests that the unification between quantum physics and general relativity has eluded scientists for 100 years because huge fluctuations in space and time mean that gravity won't play by quantum rules. Since the early 20th century, two revolutionary theories have defined our fundamental understanding of the physics that governs the universe. Quantum physics describes the physics of the small, at scales tinier than the atom, telling us how fundamental particles like electrons and photons interact and are governed. General relativity, on the other hand, describes the universe at tremendous scales, telling us how planets move around stars, how stars can die and collapse to birth black holes, and how galaxies cluster together to build the largest structures in the cosmos. Since their development, these two theories have grown more robust and have bolstered science with their tremendous success. Quantum mechanics has shown that the quantum world is replete with counterintuitive aspects, like the existence of systems simultaneously in contradictory states or particles instantly influencing each other, even at opposite ends of the universe. General relativity, meanwhile, has revealed that the very fabric of spacetime is shaped by the matter sitting upon it, and that violent interactions between bodies of great mass can create ripples in spacetime known as gravitational waves that can travel for billions of light-years to wash over Earth. Yet, there is a problem, a dark cloud that hangs over these disciplines. As these two pillars of physics are perfected, scientists are still unable to bridge the gulf between them. The two pillars of modern physics are inconsistent with each other, which means that there is a fundamental contradiction which lies in the very foundation of our laws of nature, University College London, UCL, Professor Jonathan Oppenheim said. Oppenheim is the pioneer of a new and radical theory that could finally bring together these two concepts, a reconciliation that has defied the greatest scientific minds for over 100 years. Previously, uniting general relativity with quantum physics has meant taking spacetime, the three dimensions of space and the one dimension of time, unified as a single 4D entity that is at the foundation of general relativity, and breaking it down into discrete units, or quanta. This requires spacetime to be a passive stage on which the action of the universe plays out. However, general relativity hinges on spacetime not being a static stage but rather a dynamic player in the universe's cosmic ballet, shaped by the presence of matter and energy and subsequently telling matter and energy how to move via the curvature and gravity that arises from it. Oppenheim's idea of e-waving spacetime is based upon asking why gravity should have a quantum nature like that which has been discovered for the universe's other fundamental forces, electromagnetism, and the strong and weak nuclear forces. Gravity, he argues, isn't like these other forces. After all, it is the only one of the four that can define the very geometry of spacetime, and the fields of quantum physics evolve upon this geometry. We feel gravity because matter causes spacetime to bend. Time flows at unequal rates at different locations, Oppenheim writes in a paper discussing his theory published in the journal Physical Review X, the rate at which time flows and the causal structure, the fact that cause always precedes effect. It provides may be required to have a classical description in order for quantum theory to be well formulated. That means, according to his theory, termed the post-quantum theory of classical gravity, that spacetime, and thus gravity, don't have quantum description. That's thanks to random fluctuations in spacetime, which cause changes in the flow of time, thus breaking the concept of predictability. NASA marks the 25th anniversary of the ISS with a live event on December 6th. The ISS, operational since 1998, has been key to space research and exploration, hosting 273 astronauts and over 3,300 research projects. NASA is celebrating the 25th anniversary of International Space Station operations during a live conversation with crew aboard the Microgravity Laboratory for the benefit of humanity. Space Station Program Manager. On December 6, 1998, the first two elements of the orbital outpost, Unity and Zarya, were attached by crew members of Space Shuttle Endeavour's STS-88 mission. Cabana was the commander of the mission and the first American to enter the space station. Through this global endeavor, astronauts have continuously lived and worked aboard the space station for more than 23 years, testing technologies, performing science, and developing the skills needed to explore farther from Earth. It has been visited by 273 people from 21 countries. More than 3,300 research and educational investigations have been conducted on station from 108 countries and areas. Many of these research and technology investigations benefit people on Earth, and many lay the groundwork for future commercial destinations in low Earth orbit and exploration farther into the solar system. Together with Artemis missions to the Moon, these proving grounds will help prepare NASA for future human exploration of Mars.
The Astronomy Daily Podcast.
And now some excellent jokes for you. The most scientific pet? The lab. What is the cuddliest particle known to science? The Higgs boson. Thanks for listening, everybody, and see you next week for another episode. Don't forget you can get all our episodes from spacenuts.io, and you can join in the conversation on our Space Nuts podcast group on Facebook. Bye.
The Astronomy Daily Podcast.